Alright, we're going to begin section 14.6 in this video, which is triple integrals. In spherical coordinates. So first we'll just talk about how we set up spherical coordinates. So we'll sketch our three-dimensional coordinate system. And then we'll consider some point x, y, z. We're going to label it differently though, so we'll just put a point right here. So similar to the way we set up our understanding of cylindrical coordinates. So we go down from that point directly down into the xy plane, and then we go from there to the origin. So now we're in the xy plane. We'll make this dotted line to the origin. So the three things that we're going to consider here are, we're going to consider this angle theta that's in the xy plane coming from the positive x-axis going out to that dotted line right there. We're going to consider the distance from the origin out to that point right there. And we're going to call that distance rho. Don't write it right here because we need that space right there to write something else. So put your rho right there. So it just looks like a P. And then we also consider the angle that this dotted line we made right here makes with the positive z-axis. So we're going to consider that angle right there, and that is phi. So now our point right here in spherical coordinates is given by rho, the distance from the origin out to the point, phi, the angle from the positive z-axis out to this edge of that triangle, and then theta, the angle from the positive x-axis is in the xy plane out to this side of that triangle. And this is a right triangle, so if you want to, you can put a little right triangle symbol down there. So now we need to talk about what our restrictions are on rho, phi, and theta. Rho is kind of like our r that we had in polar coordinates and in cylindrical coordinates. So it's a distance from the origin, so our rho is always going to be greater than or equal to 0. So rho is the distance from, let's call our point P. We'll call this P. From P to the origin. And rho always has to be greater than or equal to 0. Then theta is the angle measure in the xy plane from the positive x-axis to the line segment between Now I already said we were in the XY plane, but I'm going to reiterate that with these points I use because I'm going to put a Z coordinate on there of 0. So between 0, 0, 0, and this point right here would be the point X, Y, because we're still in the X, Y, Z coordinate system. This would be X, Y, 0. Between 0, 0, 0 and X, Y, 0. And theta can be anything between 0 and 2 pi. So the next phi. Phi is the angle measure from the positive z-axis to the line segment and actually, because I'm using this x, y, 0, let's go ahead and write our point that we have in. So I'm not finished with this one, but let's write our point in rectangular coordinates as well. So go back up to your picture. And for your P, we're writing it both in spherical coordinates, and then because I'm using these x, y's, and z's in our explanation, we'll also write it in rectangular coordinates. It would be the point x, y, z. So that's what makes this point x comma y comma 0, which is what I used right there. And I'm going to use x, y, z in our explanation of phi. And x, y, z is the same as our point rho phi theta. So phi is the angle measure from the positive z-axis to the line segment. And now the line segment we're considering here is between the origin and xyz. So from the positive z-axis out to that line segment right there. So from the line segment between zero, 0, 0 and xyz, and phi can vary between 0 and pi. So phi is between 0 and pi, which means phi is 0. That would be at the positive z-axis. Phi is pi is the negative z-axis, but it doesn't go beyond that. So it can go from up here all the way down to directly to the negative z-axis. But we don't, so phi doesn't vary from 0 to 2 pi, and it doesn't need to. We can get everything we need from rho being greater than or equal to 0, theta going from 0 to 2 pi, and phi going from 0 to pi. So if we need something, say for instance, that is back in the, say, has negative x and y coordinates, then the theta can handle that, because theta can take whatever figure we're trying to make and it can spin it all the way around the z-axis. So that's why we don't need for phi, and actually we'll get some redundant information if we did allow for phi to go beyond pi. All right, so now what we'll do is we'll look at some familiar figures or surfaces that we know in spherical coordinates. So let's let C be any constant. And this will help with visualization when you're going through and setting up integrals. So first, rho equals C. We want to know what that is. So when rho is just equal to some constant C, and remember we're working in spherical coordinates, so the fact that we don't see phi and we don't see theta, that says that they take on all values. So the same thing that we've discussed throughout the semester. So phi and theta take on all values, and that's just the values within their range. So for phi, that's from 0 to pi, and theta, that's from 0 to 2 pi. This is a sphere. So let's look and just try to make sure we understand. So if we just have rho is equal to c, theta gets to vary through all its values, phi gets to vary through all its values. We go back and we look at our picture. So we can use this picture as an example. So this rho is fixed at has some fixed distance c from the origin. So now at that point, if we take this and we get to take phi, and we go from the positive z-axis all the way down to the negative z-axis, what we get is we'll get a semicircle. And then we take that semicircle and let theta spin around the z-axis. Then that semicircle is going to trace out a sphere. So that's why rho equals c will give us a sphere. All right, so let's look at what theta equals c will give us and what phi equals c will give us. So theta equals c. Now remember, if we don't see rho and phi appear, that means rho and phi take on all values. So rho and phi take on all values. And for rho, that's rho is greater than or equal to 0. And phi, that's phi is between 0 and pi, is what we call half plane, quote unquote, half plane along the z-axis. And so we don't have to keep drawing over and over again. I'm gonna go back to our picture from the first page. So phi is fixed at c, theta is fixed at c, and rho and phi are gonna take on all values. So what do we have there? So now theta, say for instance, is stuck right here. It doesn't get to move. So this theta is stuck at that point. So now what happens is theta is stuck right there, but phi, what it does is it takes on, so say for instance, for now we'll keep rho where it is as well. If theta is stuck right here and phi takes on all values, what phi will do is it will trace out, it will end up tracing out a semicircle going from the positive z-axis down to the negative z-axis. But then what happens is we let the radius of that semicircle, which is our rho, we let that go on to infinity, which means we're just going to get, when we have something that's going out forever, then that it ends up just being a plane. But we call it a half plane because it doesn't get to go behind the z-axis. It's all stuck. So a plane that's basically coming out of the z-axis and is stuck at whatever theta value it is, but phi takes on every value and rho takes on every value. So we get a half plane there. And then next, so half plane along the z-axis. Next, we talk about when phi is equal to some constant c. And so because rho and theta don't appear, rho and theta take on all values where rho is greater than or equal to 0, and theta is everything between 0 and 2 pi. So this one we have some different cases as to what we're going to encounter. So first thing we'll get is we'll get the positive z-axis, if c is equal to 0, we'll get the negative. We'll now go over a couple of these. So as we go through, let me just write down 2 of them, then we'll go over these first 2. We'll get the negative z-axis if c is equal to pi. Actually, we'll do the first 3. And then we'll get the xy plane if c is equal to pi over 2. So let's look at those 3 and then we'll do a couple more. So c is equal to 0, c equals pi, and c equals pi over 2. So remember, this is phi that's been that's fixed. So now phi is the angle from the positive z-axis. If phi is fixed at 0, so phi is stuck. We're stuck on the z-axis, and rho gets to vary from 0 to infinity, and theta. So that's just going to give us the entire z-axis, and then theta gets to go from 0 to 2 pi. We're just spinning around in a circle, but we're stuck on the z-axis. So we'll just get the positive z-axis in that scenario. So then the next one that I did was if phi is equal to pi. So phi is equal to pi means we are all the way down here on the negative z-axis, and phi is stuck at pi because if phi is always equal to pi, rho is to take on every value. So it's going to go from, the rho actually goes from 0 to infinity, but it's pointing in the negative direction already because of the phi. So it's still going to go from 0 to infinity, which will give us the entire negative z-axis, and then theta will go from 0 to 2 pi, but we're stuck on the negative z-axis. So we spin around, but we're stuck on the axis, so we just get the negative z-axis. Now, if we take phi and bring it down all the way to pi, that puts this in the xy plane, but we're stuck there. Now, at that point, rho will go all the way to infinity, and then theta will spin around the entire xy plane, and we'll get the whole xy plane there. All right, next we'll get the upper nape of a cone. If c is anything strictly between 0 and pi over 2. And then we'll get the lower nape of a cone. If c is anything strictly between pi over 2 and pi. But remember, c is going to be fixed between there. So I'm not saying that c is going to vary between there, but say you had any fixed value c that's between these two numbers, then you're going to get a cone. So let's look at those last 2. So c is something between 0 and pi over 2, and then c is something between pi over 2 and pi. So our picture right now is phi is at some c between 0 and pi over 2. So now if we allow rho to go from 0 to infinity, and then theta to spin around the z-axis entirely, we're going to end up spinning this little line, or really it'd be an infinite line, or array, because it's going to start at the origin and go out to infinity. We'll spin that ray around the z-axis and we will get a cone. Now if we took phi and we came all the way down and we were at anything above pi over 2, meaning we're going to go below the xy plane. So say for instance we pulled phi all the way down here, then rho still gets to go out to infinity. So we would have a ray coming from the origin. Theta would spin all the way around the z-axis and we would just get a cone that was below the xy plane. So you'll see a lot of these different equations that you go through and do problems. So it's useful to be able to know when you see whatever phi is equal to pi somewhere, you'll know, okay, that's just the negative z-axis. Or you see phi is equal to pi over 4, for instance, you'll know that that is just the upper nape of a cone. All right, so I'm going to stop this video here, and then in the next video we'll talk about how to convert from rectangular coordinates to spherical coordinates and vice versa.